Geraint, our question for this week, let's get straight to it. What happens if you fall into a black hole?
That is a rather excellent question. And I've just finished teaching general relativity to our class here. And it is one of my favorite parts when we have to talk about this notion of falling into a black hole. Then things get a bit weird when you start talking about white holes, etc. And
Yeah.
But let's deal with this question, and we'll deal with it from a purely general relativistic point of view. There's been a lot of talk about quantum mechanical things that can happen related to Hawking radiation and firewalls and all these things you can encounter. But let's just do the good old-fashioned relativistic, drop somebody into a black hole.
What does Einstein say?
What does Einstein say?
All right.
Well, the story, of course, doesn't start with Einstein. Okay. It starts with Carl Schwarzschild.
Okay.
Right? Yeah. So the story goes that Einstein derived the field equations for general relativity in 1915, and he looked at those equations and he just went, this is hard.
Good luck, everybody.
Yeah, but in German, of course.
Yeah.
And he wasn't sure if there were actually any analytical solutions, i.e. solutions you can write down in the form of an equation.
Right.
And it was the following year that Carl Schwarzschild wrote down the equations for the gravitational field outside of a spherical mass distribution. And so that describes the gravitational field roughly outside the Earth or the Sun, etc. But what you can see in Schwarzschild is that you can take that spherical mass, you can just make it smaller and smaller and smaller, and you keep getting the gravitational field, and you get below a certain point, and you hit this thing called the event horizon, where weird things start to happen. And then essentially, once the mass is below that, that's when no forces can stop it, and it collapses down completely to a point called the singularity, and you then have this thing, the black hole, right? So this is the Schwarzschild black hole. So it's not rotating, has no charge. It's just a mass producing a gravitational field.
Right. There's an interesting point there. So actually, if you went up above the atmosphere of Earth and you wanted to use Einstein's theory of gravity to describe the gravitational field of Earth, it would be the same thing, the same equations that Schwarzschild derived. And so if you're working out what happens as you fall towards a black hole with the same mass as Earth, and what happens if you fall towards Earth, you get the same answer until, for Earth, you hit the surface.
Yeah.
Right, hopefully nice and slowly with a parachute or something. So it's we've got to shrink that mass down before we start to see the really weird stuff.
That's right. So what we have to do is we have to move into what's known as the strong gravitational field.
Right.
Okay. So to answer this question, let's make you the faller.
Sure.
Right. So I'm going to be an outside observer.
Okay.
I'm going to hold on to you, let you go.
Okay.
Right. So I'm on board a rocket ship, and I've just dropped you out the window. So as you said, when you start falling, I'm not going to go too close to this black hole thing. It's dangerous. That's why I've sent you.
Sure.
When you start falling, you just start falling, right?
Yep.
So what we have to do is we have to consider the fact that I've got my viewpoint and you've got your viewpoint, right? So we can't confuse the two. So let's just do your viewpoint first.
Sure.
Right? So you start falling, right? I accelerate away from you, and you start falling, and you just continue to fall. But you're in a gravitational field, and you're falling in the same way that an astronaut is falling towards the Earth when they're orbiting. You're in free fall.
Yep.
So you essentially feel like you're weightless.
Yeah.
Right? So
this is one of the amazing and foundational things of Einstein's gravity. This was his major. That free falling and no gravity are indistinguishable.
Absolutely. So actually, you fall and you get to this place, the event horizon, and you just sail on straight through.
Right.
Okay. So
good.
In you fall, right? We'll come to what you see in a moment.
Right.
But as you get closer to the center of the black hole, we have to take account of the fact that you're an extended object, right? And that means that different parts of you will be feeling different gravitational pulls.
Right.
Okay? And so
I'll drop in feet first.
Feet first. That? Yeah. So what you will get is that the gravitational pull on your feet will be stronger than the gravitational pull on your head.
Because it's closer to the center. Right.
So that starts to pull you in this direction.
Right.
Also, there's a gravitational pull on your arms is different to the gravitational pull in the middle because you are falling radially, right? And so these points get pushed together.
Right. That shoulder's going to the center and that shoulder's going to the center.
And the middle is going to the center.
Yeah.
So this is this thing called spaghettification, right? What happens is you get drawn out, and eventually the chemical bonds that hold you together are overcome by these forces, and you get pulled apart, right? And
that's the end.
Right,
what a way to go.
I mean, I think it'd be kind of interesting.
Yeah.
Right, but we'll come back to what you see, right? So let's now take my viewpoint.
Okay.
I'll let you go. I see you fall, so you accelerate away from me, right? Everything seems fine, right? You're falling. Well, when I say fine, of course, I have just dropped you into a black hole. But everything seems fine, and you're falling. I just noticed nothing strange until you start to get a little bit closer to that thing, the event horizon. Now, as you get to event horizon, your light is still traveling towards me, but it is having to struggle, right? It too has to sort of struggle against the gravitational field to get out to me. So what starts to happen is that the light from you starts to lose energy by the time it reaches my eye. Right. So
suppose I'm holding a strobe light that's sending it's a white light and it's going at 1 second. Beep, beep,
yeah.
Beep,
I'll tell you what, let's pretend you've got a blue shirt on.
Oh, perfect. No.
Yes. So what I'm seeing is that this blue light...
This is grey, actually. Well...
Yeah, all right.
It's definitely not gold and white. Let's just say that for the internet.
Well, let's pretend it's blue. That blue light, its wavelength is getting longer, so I see your shirt colour start to turn to red. Right. Okay, and then all of your light is being red shifted. Okay. So let's give you that light, right? So let's make it a blue light, and I've seen that blue light get shifted towards the red. Yep. Now you said that light is flashing at 1 flash per second. When
according to me, I've got a clock and the whole way in one per second.
That's right. But that light again, I'm seeing coming from you as you fall in, is struggling to climb out to the gravitational pull. And there's also a gravitational time dilation effect, right? And so what happens is I start to see those flashes, instead of being once per second, once every second and a half, once every 2 seconds, once every, etc. And these effects get stronger and stronger and stronger as you approach the event horizon.
So if I give you I'm doing okay so far, eventually what you'll see is a sort of slow motion red.
So it gets really bizarre when you get really close to the event horizon, right? Your red shifting gets larger and larger, okay? The flashes, the time between flashes gets longer and longer until, right, I basically see you freeze. Like that, right?
Right.
So
I'll pull that face. I'll make sure. Yeah. Good.
So actually, I never see you cross the event horizon. I see your image frozen, right, just before you hit it. Okay. So what's actually happening is that light is having to battle harder and harder to reach me from you as you fall, and that when you get to the event horizon, then it basically means that it takes an infinite amount of the light's energy. So the red shifting goes to infinity, the flash freezes, so I never see you cross. Right. And if I could see the clock on your watch, the time on your watch, I should say.
That's the one.
I would see that the second hand slowing down, and it would stop at a certain time. Now, at that time, you would say, oh, I've crossed the event horizon, happily sail on through. But I would never see you cross. Right. Now, this is kind of cool, and it really confused a lot of people. I mean, it confused Einstein. Yeah. Right. He actually wondered if black holes could ever form, because if you look at this picture where things never cross, then how can a black hole accumulate mass, etc.
Yeah, it would seem like it would take, if you were trying to build one, you would start lowering stuff onto the construction crew starts lowering some more mass, and it takes an infinite amount of time for it to get into the middle.
But we're talking about viewpoints, right? So from my viewpoint, you've never crossed, but it's not like I could fly down and grab you and bring you back, right? Because if I wanted to do that, it would take, say I had a fishing rod, and Luke, catch this kind of thing. Right. It would take an infinite amount of time for my fishing rod to actually reach you. But again, you've already got. So I've seen this in science fiction stories, that the thing that they also get wrong is that they turn my experience as an observer into your experience as an observer.
Yeah, as if I'm there going, "Mrrr," yeah.
And that you, before you cross the event horizon, that you see the infinite future of the universe play out because you're trapped there on the surface.
Right. There's no slow-mo. I'm never in slow-mo.
You're never in slow-mo, right? So you don't. You sail on through. You're still receiving light from the outside universe. You basically see the universe pass and then splat. You don't see the entire. If you see a finite amount of the universe, splat.
So I don't get to see the end of the universe.
Don't get to see the
I think I remember asking you this in general relativity class when you were
and I
when
told
you were lecturing me. You gave the right answer, and we looked at the coordinates, and no, there is a last light. There's a last light ray you'd see, even if you could live all the way to the singularity. I was listening.
Yeah, excellent. So now I'm on the outside. Let's pretend you've crossed the event horizon.
Okay.
Right? I've no longer any contact with you. I know that your future is at the central singularity. And so the question is, you've got a finite amount of time left.
Yeah.
Can you extend that amount of time?
Okay. I put on a jetpack.
Yeah, let's put it on before you fall in.
Sure.
Right.
I was just falling in with it, but now I've realised something weird's happened.
Right.
And I'm going to try and at least extend the amount of time.
Right. So, turns out that there is a maximum amount of time you can spend falling below the event horizon.
Right.
And that is the situation of if I dropped you right at the event horizon and let you go,
right,
it's equal to pi times the mass of the black hole in appropriate units.
Yeah.
Right. So that's the maximum amount of time, and anything else you do to try and change your path from that particular path reduces the amount of time you have.
Right.
So if you fire a rocket pack as hard as possible, right? Okay, you think, right, and you point outwards, you blast it outwards, you think, right, this is going to give me more time. It actually reduces the amount of time you have. There's additional time dilation effects that kick in that mean you have less than pi times m amount of time before you hit the central singularity.
Okay.
So this is the there's no point in struggling. You're just going to make it worse.
Well, there is something. I mean, you still can get on that. So the way I think of this is, and there's a lovely paper that you wrote with
Juliana.
Yes.
Juliana Kwan.
Yep. We'll link it below. There are different paths that you can take towards your doom.
Yes.
So which correspond to how far away from the black hole were you dropped.
That's right.
So I dropped right on the edge, or at the edge of the event horizon, or up to sort of infinity. And if I was dropped, as you said, a reasonable distance away, and I'm falling in, I think, oh no, I better maximize my time. The thing I've got to do is to get on the path of the person who was dropped right at the event horizon. I can do that with a rocket ship.
That's right.
Rocket pack.
You can adjust yourself onto that path, but you can't do any better than that.
Yeah, that's
can't do anything.
Okay.
Yeah, and I should point out that if any of my 2019 GR students are watching this, they will know that question 3 of the assignment this week is to calculate just that thing.
Oh, excellent.
Yes.
Well, good luck, everybody.